Okay, so in the last video, I showed you how we got to this equation, and now I'm going to show you what certain cases this applies to. So quickly, so that you remember, we started off with an energy balance. We started off with a complete energy balance, and then we did simplifications where we assumed that, this is a steady state system, so there's no energy accumulation inside the system. Any energy that enters the system must leave somehow. And we also made an assumption that the kinetic and the potential energies of the system are negligible, so they're almost zero. And I've talked about why in the previous video. We also assumed that, there was no shaft work, so let's assume it's zero or negligible. And we also made an assumption that we don't have any chemical reaction or nuclear energies that we need to consider. And so it is zero. And this then boiled down the equation to the heat exchange of the system with its surroundings would then be the energy difference between the enthalpy of the fluid coming in and leaving the system. And I said we can then simplify that to Q equals mCpΔT. But I was just going to tell you when this applies. So this applies for ideal gases. Obviously, if you have steady state, no energy accumulation with negligible kinetic and potential energy changes, no shaft work, no energy generation, and negligible viscous dissipation. Now, next slide, I'll explain the importance of assuming negligible viscous dissipation. And I think this is one of the things that a lot of students get confused by, because when they study thermodynamics or heat transfer, they never think about viscous dissipation. And only when they study fluid mechanics is when they actually start understanding what viscous dissipation is. And I don't think that these two courses that you might have had in your university never really met. You never really got to see the interface between the thermodynamics and the heat transfer side and the fluid mechanics side. You just learned how to apply these different energy balances when you were trying, for instance, to solve for something. So if you were solving for a pump, you used the energy balance you learned from fluid mechanics. But when you were solving something for heat transfer or thermodynamics, you get to use this equation. But you never really appreciated how they're actually coming from the same energy balance. And I hope that maybe I can do that, but I'll leave that for the next video. It's something I'm passionate about, and hopefully I can relay that information in the next video. Anyways, again, to use this equation for the ideal gas, I said we need to be able to make these assumptions. And also I want to note that pressure or density changes of the ideal gas do not affect this relationship directly, since for an ideal gas, enthalpy depends only on temperature. However, such changes may be associated with fluid acceleration or frictional effects, and if they result in significant kinetic energy variations or viscous dissipation, then obviously additional energy contributions arise, and this simplified equation is no longer valid. Therefore, pressure or density changes are acceptable only when they do not introduce significant mechanical energy or irreversible losses within the system. And when I talk about negligible viscous dissipation, you'll get to understand this more. Okay, so for incompressible fluids, you could also apply this simplification. And the simplification is really just from using or having to know the enthalpies of the liquids at the inlet and the outlet states, and you could just use this simplification, mCpΔT. So in order to use that for incompressible liquids, again, it has to be at steady state, so the system has no energy accumulation and negligible kinetic and potential energy changes and negligible shaft work and no energy generation and negligible viscous dissipation. However, unlike ideal gas, in order to use this simplification for incompressible liquid, then pressure changes and volumetric mass density changes from the inlet to the outlet must also be negligible. And hopefully in the next slide, when I talk about viscous dissipation, you can better understand that. So without further ado, see you in the next video.